Alright, in this video clip we're taking a look at section 4.2, which discusses direction fields and numerical methods. We start with the definition of a direction field. So here's one definition we can use. A direction field, which is also known as a slope field, is a graphic that represents the flow or movement of a solution to a first-order differential equation. Now, when we refer to a first-order differential equation, that means we're simply taking the first derivative in the differential equation, not the second derivative or the third derivative, for example. At each point on this graphic, we represent, via the differential equation, the slope of the solution curve. In other words, the differential equation in a first-order differential equation tells us the slope as a formula for the function that we're looking for. That slope will represent the slope passing through any point that we're interested in on that graphic. So let's take a look at an example of this very simple differential equation, dy dx equals x. So that means that at every point on the plane, the value of x is telling us the slope of y. The derivative of y with respect to x is the value of the x. The slope at each point is simply the value of the x-coordinate of the point. Now, the way this would manifest itself as a graphic would look something like this. Here's your plane, and what we notice is along the y-axis, which simply means along the axis where all of the values of x are 0. The values of x are 0 means the slope of y at those points along the y-axis is 0. So the slope values are 0 means that the tangent lines we would draw to that curve y would have slopes of 0. And we draw these little dashed lines, short little lines with slopes of 0. Now, if we move out, say to the point where we're at x equals 1, well, then x equals 1 represents the slope of the tangent line to the curve y. So at all the values of x being 1 here, we draw our little direction lines with a slope of 1. If we were to move out to x is 2, now 2 is the slope of that. That means when we draw our direction lines here, they have to be steeper. They have to have a slope of 2. So they'll go up steeper. We don't have to make them longer, we just have to make them steeper. Now, on the other hand, when we go to the other side of the graph, say we're at the place where all the values of x are -1, this vertical strip right here, then the slope of y, the slope of the tangent lines, is -1. That means as we draw our little direction lines here, we draw with slopes of -1, going down 1 and over 1. If we were to move out to -2 on the x-axis, all the points here that are along the strip where x is -2, the slope is -2 for y. So we draw our direction lines with a steeper slope downward here. And so what we see when we think about this is, if we're at any particular point, suppose we're right here, for example, we can see that the slopes here are downward. So our curve is going to be going downward, and it's going to be pushing to the right. But as we go to the right, we start to flatten out, and as we pass through the y-axis, then our slopes go up. And so our curve looks like that. And so a solution curve to this looks something like this according to the direction field. Now, if you think about what the solution is to this very simple differential equation, what function is it that you take the derivative of to get x? Well, you take the derivative of 1/2 x squared plus any constant. And you know that 1/2 x squared is a parabolic shape, and that's what we're seeing in this direction field. Okay? Let's look at a second example here. We'll take a look at this differential equation now. dy dx, the slope of y, is simply the y value of a point minus the x value of the point, which simply means that y minus x is 0 along the line y equals x gives you that the slope of this curve y is 0 along the line y equals x. And I've indicated that here on our direction field. Here's the line y equals x, all these points where y equals x, and the slope of the curve that is a solution would be 0. So we draw horizontal lines, lines with slope 0. Now, what happens as we move away from this line, y equals x? Well, if we're on this left side of the line y equals x, those are going to be the places where the value of y is larger than the value of x. So over here, the slope is going to be positive. Y is going to be larger than x on this side of this line. Now, if we're very close to the line, however, the value of y and the value of x will be very close to each other, and while y is bigger than x means this is positive, this will still be very close to 0, meaning when you're close to the line, you're very close to being horizontal. You're just slightly positive. But as we move further away, say we get way out here, the value of y is much larger than the value of x. So the slope is much more positive. Almost getting steeper and steeper the further away we get from that line. And of course, if we're on the right side of this line, meaning down here, well, then the value of x is larger than the value of y here, and so y minus x is going to be negative, which means as we move over to these points, our slopes are going to go downward. And initially, they're downward slightly, but as we move further and further away, they get steeper and steeper, pointing downward. Okay? So we're steep up here, steep down here, slightly down here, and slightly up here. Now the interesting thing is here, when these are slightly up, they're actually driving us toward this line, and this line then becomes an equilibrium line. That simply, again, is where y minus x is equal to 0. And this equilibrium can be analyzed in the following way. If we're to the left of this equilibrium line, our solutions will drive towards it, pushing us onto the equilibrium line. But if we're to the right, our solutions will drive us away from it. And so we classify this equilibrium line as what's called a semi-stable equilibrium line. It's stable in the sense that if you're from the left, you'll approach it and you'll stabilize down to the line. But if you perturb yourself off that line just a tiny bit to the right here, well, then the solution takes you away from it. And so that's what's meant by a semi-stable solution. Now, we're not going to worry too much about the classification of equilibrium points or even finding equilibrium points or equilibrium lines. It's just an interesting thing to note that exists. Okay? All right, so now let's go on to something we do want to know a little bit more about, and that's this idea of a numerical method of solution. The numerical method of solution that we have in this course is called Euler's method. And so I want to show you how Euler's method is working. Okay? First, we define what Euler's method says. Okay? It says, given a first-order differential equation, that is, a first derivative appearing in the differential equation with an initial condition, then we can define the approximation to our solution as the set of the following points. And these are going to be points that we iterate through to get. And the way we do that is the following. The iteration process is that the nth point for x is simply the previous point for x plus a value called h, where h is going to represent the step size of our approximation process, very much like h was used when we were doing integration and cutting up into intervals, an interval of integration. The y-coordinate at the nth value is going to be the previous y-coordinate value plus the step size times what the function tells you to do at the previous point. And so we'll have to go through and explain what that's saying. But your iterations are n starts at 1, 2, 3, and so on for however many iterations you choose to do in your approximation process. So let's show this process in action, and you get a better idea of what this is all saying. In problem number 94, we're asked to use Euler's method over an interval from 0 to 1 with n equals 5. We want to do 5 approximations to approximate the solution to this differential equation, that the slope of y is simply negative 3y with the initial condition that when x is 0, y is 1. Okay? Now, that tells me that n is 5 over the interval from 0 to 1. Therefore, the step size is simply 1 minus 0 over 5, a step size of 0.2. So we set up the iterative process over here. These are the initial values we're given: x naught, y naught, 0 and 1. Now we have to iterate step by step through our solution to get the approximations. So here's what we do. x1 is simply the x naught value plus h plus 0.2. So 0 plus 0.2 gets us to 0.2. y1, according to this iterative process here, is the previous y value, y naught, plus the step size, 0.2, times the function evaluated at the previous point. So the function, again, is negative 3y. That's telling us the slope. So that's negative 3 times the initial y value from above, y naught. And that evaluates to 0.4. Okay, so we started at the point 0, 1, and the second iteration of the, or the first iteration of this gets us to the point 0.2, 0.4. Okay, now do another iteration. X sub 2. We simply, to get x sub 2, take the previous x value and add the step size to it. So 0.2 from the previous plus the step size of 0.2 gets us to 0.4. Y sub 2 is the previous y value, the 0.4, plus the step size times the function evaluated at the previous y value. So 0.4 plus 0.2 times the negative 3 times 0.4 that's indicated from this function again gives us a 0.16. So now we're at the point 0.4, 0.16. Continuing the iteration, at x3 we get 0.6, that is the previous x value plus 0.2. At y3 we take the previous y value of 0.16 plus the step size times the function, negative 3 times the previous y value, we get 0.064. At x4, we add 0.2 to the x3, the step size added, to get us to 0.8. y4, the previous y value, plus the step size times the function evaluated at the previous y value. Now we get 0.00256. And finally, adding another 0.2 gets us to 1 for the x5. We're at the right end of our interval. The y5 is the previous y value plus the step size times the function evaluated at the previous y value for this evaluation of y. Okay? Now, if we were to plot what these look like, 0, 1 would be there. 0.2, 0.4 would be there. 0.4, 0.16 would be there. 0.6, 0.064 would be here. 0.8, 0.0256 would be here. And 1.0041 would be here. So we're seeing a solution that's going along in this fashion. Okay? Now think about what the solution to this differential equation actually looks like. Okay? Think about the solution to y prime is negative 3y. What would you take the derivative of? What function would you take the derivative of to get negative 3 times itself? Well, wouldn't that simply be the exponential function whose exponent is negative 3? The derivative of that is simply negative 3 times the original function. And so look at this. This is supposed to be the function we're graphing here, e to the negative 3x, and that's what a decreasing exponential looks like. Goes through at a height of 1, and it decreases down to, very quickly, the horizontal guideline of the x-axis. Okay? All right, let's take a look at one more example of this to conclude our discussion of section 4.2. Okay, in problem number 98, we're looking at this little simpler differential equation. Now, y prime is 2 times t, where the initial condition is when t is 0, y is 0. So again, the initial value, x naught, we'll use x's instead of t's when we do the iteration, it's fine. X naught or t naught, doesn't matter what you call it, is 0, for y naught is 0. The step size is going to be the same as prior, because it's still from 0 to 1, with iteration of 5 steps. So 0.2 is our step size. So as we iterate from x naught to x1, we add 0.2. When we go from y naught to y naught, 1 now, we take the previous y value, the y naught, plus the step size, times the function evaluated at the t value, which is this one here, the 0.2. So that's going to be 0.2 times 2 times this 0.2 from here. So we get 0.08. The next iteration, we add 0.2 to the step size of 0.2 to get 0.4. The next y, we take the previous y plus the step size times 2 times the previous x value, or the x value of this thing. Okay? So now we get 0.24. Increase the step size again by 0.2, we get x up to 0.6, or think of it as our t if you want. Our y value is 0.24 plus the 0.2 times 2 times 0.6, the 2 times the x or t value. We get 0.48. x4, we get 0.8. y4 is the previous 0.48 plus 0.2 times 2 times the x value. We get 0.8. And finally, at x5 is 1. y5 is the previous y value of 0.8 plus the step size times 2 times the x value. We get 1.2. So think about what these would look like if we were to plot these. We start at x naught, y naught is 0, 0. And we'll think of this as t versus y. Think of that as x's if you want, or t's. Okay, at 0.2 we get a 0.08, very small. At 0.4 we get a 0.24. At 0.6 we get a 0.48. At 0.8 we get a 0.8, sorry. And at 1, we get a 1.2. So we're getting this shape to our solution. Okay, what does the solution to y prime equals t2t look like? dy dt is 2t, means y is t squared plus some constant, right? And in this case, since the initial condition is 0, 0, that constant is 0. So all we're seeing here is the solution is t squared. Okay? So hopefully you can see the use of the graphing of the direction field and Euler's method that we can generate a step-by-step picture of a solution flowing through the direction field are simply meant to replace the process of actually finding the solution. If we can find the solution, that's great. We use the solution. When we can't find the solution, that's when looking at something like Euler's method to look at the flow through the direction field can help us to better understand the solution. Okay? Again, if you can find the solution, you should. That'll be the preferred method with the best understanding of what's going on. But we use approximation techniques in direction fields in the cases where we can't explicitly find those solutions. All right, that's it for section 4.2. Go ahead and try those homework problems and see if they'll make sense to you. And now in section 4.3 next time, we'll actually be solving these. So we won't worry about approximation techniques anymore. We'll be after these exact solution forms.